Okay, this is Sarah Bagley with Chapter 9, Teach the Doc on Gases. So the first part of our Teach the Doc has complete the following conversion table. And 680.0 millimeters of mercury, and you have to convert it to kPa, torr, and atm. So you get 90.7 on your first one, and you get 680 on torr, and 0.895 on atmosphere. Suppose a gas has an initial pressure of 2.0 atmosphere. What happens to the pressure if the volume is doubled? Assuming the temperature in moles of gas exert a lower pressure, since pressure and volume are inversely proportional. And you can see I wrote that out. And of course, I will attach this to the video link as well. Now, suppose a gas occupies 1.5 liters at a certain temperature and pressure. What happens to the volume if the number of moles of gas is tripled? Volumes of gas and numbers of moles are directly proportional. So the volume triples too, and it becomes 4.5 liters. And you can see I have that answer written out. And now we're going on to the ideal gas law. Number 4, which has a lot of stuff here, which you'll just have to see my work that I have written down that I'll attach. An ideal gas sample occupies 1.5 liters at 25 degrees Celsius and 741 millimeters of mercury. How many moles are there in this sample? And my answer that I got is the number of moles is 0.0598 moles. And it's really hard to see because I have so much different work, but you can see it right there. And again, I'll attach this. And the next thing is, what volume would the gas sample occupy at standard temperature and pressure? And the answer to that is the volume would be 1.34 liters. And you can see that answer is there. Okay, what is the equation that relates the density of a gas to its molar mass? And that is density equals molar mass times pressure divided by R, which is the different constant that you find. I'm trying to remember what that's called. The ideal gas constant. And times pressure. So molar mass times pressure divided by ideal gas constant times temperature equals density. And that's the equation right there. And what is the molar mass of the gas if its density at standard temperature and pressure is 0.901 grams per liter? And after plugging it into the above equation, my molar is 0.19 grams per mole. Last page. Which component, hydrogen gas, oxygen gas, or CO2, exerts the highest partial pressure in a gaseous mixture made of 0.50 moles of hydrogen gas, 0.49 moles of oxygen gas, and 0.48 moles of CO2. Hydrogen is 0.50 moles, which is more than oxygen gas and CO2, so hydrogen gas has the highest partial pressure in a gaseous mixture. And I have my answer written out there. Which of the following mixtures exerts the highest total pressure? So I added all of these up, and A comes to 1.5 moles total, B comes to 1.4 moles total, and C comes to 1.6 moles total. So C has 1.6 moles total, which is the highest amount of moles, which is the highest total pressure, and that's the answer right there. C has the highest total pressure. And the next question, calculate the mole fraction of each gas from this word problem. A 25.0 liter cylinder contains 3.00 grams of hydrogen gas and 14 grams of nitrogen gas at 25.0 degrees Celsius. So, and I have this all written out somewhere. Where's 9? So you have to find out what their moles are. And I did a whole bunch of calculations that you'll see when I attach it. But the mole fraction of hydrogen 2 is 0.75, and the nitrogen 2 gas fraction is 0.25. Right there. Calculate the partial pressure of each gas. So the partial pressure of hydrogen 2 was 1.46 atoms, and the partial pressure of nitrogen gas was 0.489. I don't know why I said atoms, I meant atmosphere. 0.489 atmosphere. And I have that written down here, and I will attach the sheet that I did all of my work on because it was not enough room on this. But these are the sheets that I have all the calculations on. All the calculations are on these sheets, and I will take pictures and upload them in the same link as this video. So you will have all of this to peruse. And that is the end of my Teach the Doc video because my kids are not going to stay quiet any longer.